I would like to share some research that I have been doing last several years with my students and funded by Caltrans and also METRANS. So what we are trying to do is trying to make the road smart. Now, if you take a look on this one, we are very much kind of used to of the traffic in LA, and I like this quote from Mr. Void that you have to basically go to a meeting about several hours earlier and sitting in the traffic to enjoy the sunshine of the LA. So now the point that I like to make here at this place that everything surrounding us getting smarter. So you have a smartphone, smart TV, smart home, and all these things. So now the question is that how smart our road is. So do you think it is smart or not? So let's see what are the instruments like Caltrans and others are placing to right now to sense, because to make a smart decision you have to sense. So let's take a look. These are the technology that you will find in the street right now. In my left you can see that inductive loop detector. So how many of are you familiar with, have you seen something like this in the street? I think all of you. So do you know what does it do? Any idea? So just to give you in short, it has a inductive loop. So that has a that basically pass a DC voltage, and then when a car passes on top of it, it can detect it. So that's kind of technology that we used right now. So this is the most used technology in the road nowadays. Now, any idea that when this technology, we started putting in our road? 10 years ago. Okay. So anybody else? Okay. So let me give you a understanding of how old this technology is. It started around early 80s. So I'm pretty sure not most of you was born at that time. So now let's try to think about 1980 to until this point, around 40 years, isn't it? Around 40 years. So in around 40 years, the phone that you have at this moment in your pocket was a supercomputer in 1980s. So you see that things have changed so much. So you have a supercomputer with you that could be, the smartphone right now with you in 1980s. So, but still the technology of 1980s is in our road. So I like to make a point how smart we are still in making the smart road. So beside that, we are also, the transportation industry is trying to put a magnetic sensor that are much more smaller. So this is the trend right now. This is not a full scale yet, but this is the trend that we like to basically see, where it becomes very small footprint. So here you can see that we have a footprint of 4 feet by 6 feet, so on. Here size of a quarter or bigger than that. So this is what we like to see in a smart road. And my research, that what we are going to explain today, also based on the magnetic sensor. And this technology can detect the vehicle and has much smaller footprint. Now, beside that, the transportation industry also put like radar sensor to detect the speed, and also the video cameras to give you tickets. So these are the sensors that you see nowadays that in our smart road. Now the move is to go towards the smart road and remove this, 40 years old inductive loop with the size of a quarter-like system. Now, you can ask me, what is beside the size, what are the problems with the inductive loop right now? If you just read at the top couple of lines, you'll see that Federal Highway did an investigation of the existing loops, inductive loop in New York, and they find it out of 15,000 loop, there are only 25% of them are active or functional. 25% are not operational at any given point of time, and it takes around 2 years to fix them. So you can see that 1/4 of the sensor, 15,000, is not working, and it takes around 2 years to fix them. So to answer this question, to basically make our road smart, there are so this is the research that we have been doing. It's not only me; there are many other researchers working on this area. So the idea is to it's in pavement, vehicle detection and identification. So technology is mature enough to detect it, and in my research group, we are trying to do the identification. So what is the difference between the detection and identification? So the meaning of detection is that you can detect a vehicle. So it could be any kind of vehicle and so on. The meaning of identification is like, I am Mohammad Mozumdar and you are X and you are Y. So that's identification, and that's very tough because we have so many cars there. How you can identify each of the vehicle, and there are many applications of that. So we are trying to, in my research group, we are trying to focus on detection plus identification, and our major focus is mostly in identification. Now let's take a look of the technology that we are designing compared to the traditional technology that we have in the induction loop and the new smart system. If you take a look on the components of the system, you'll find it out that it's, first of all, there's a small footprint. Secondly, the number of components are reducing. So on the top you can see the existing inductive loop system, and so this you can think about the road. So this is the road where we have the inductive loop wire, and there is a pull box, and this need to be connected to the controller on the sideway. Whereas the developed new system that we are working on is very small magnetic sensor, and there is no physical connection because everything nowadays is wireless. So that's what also we are trying to use it. There is no physical connection. So it's wireless, and it's connected to the access point, which is much smaller to the traditional system. So the benefit that we get into the new system is smart footprint, and also the long cables lengths are eliminated, and also the sensor and controller are deterred. So for example, you have any problem with the sensor or the controller, you can change it without touching the another one. So there are many benefits that you get out of it. Now, if you like to take a look, what is inside of a sensor? What is inside of a sensor that we are designing? If I like to give you an idea, this is the architectural diagram of a sensor inside. So as I said, this sensor use the magnetic signature of the vehicle. So that's why you have a magnetometer here, and that's pretty small. And then it has a microcontroller, and it has also an antenna for communication. So it has also the RF chip for communication. So that's why you see that it's connected to the antenna. Meaning is that it has a processor, and also it has a communicator that can communicate with the controller on the side. And then it has also obviously need power, so it has the battery. And when you install it under the highway, underneath the pavement, you don't like to change the battery every like couple of days. That's not feasible, isn't it? Who is going to change the battery? It's impossible. So we like to design the system that can last many, many years without changing. And secondly, is there any way we can also basically give the power? So any idea how can we give the power without basically connecting to the direct power supply? So the answer is, if you can scavenge the power. So what is the meaning of energy scavenging? So the energy scavenging, the most familiar one that you are known of what? Solar, isn't it? So we use the solar, but since it is underneath the pavement, we cannot use the solar because there is no solar there. So, but we can use the vibration of the car, because when a car passes, if you just stand beside the highway, you will see the vibration of the car, how fast they go and kind of vibration it makes. So we try to also have a energy harvesting, scavenging components that can scavenge the power from the vibration of the car. So literally this node can basically last year after year. So the test that we have, without any energy scavenging, it can last around 7 years. With the energy scavenging module, it can last, outlast the road. So year after year, it can do the operation. So this is a single component. So if you try to take a look how the whole system will look like, whole system of the smart road will look like. So if you take a look here, that in our road we are going to put these small micro sensors. For example, you have to put 2 of them, because if you put 2 of them, then you can also not only detect or identify, you can also detect their speed. And for example, if you put a pair in each of the lane, and then they are connected wirelessly to the roadside substation, and which is very small box, and this could be powered by a solar cell. You can see that you could have a solar panel here that could power the system. And then this system base station could communicate with the regional center by using GPRS, that means data connections to the regional center. And many of these substations can connect to the regional control center to collect the data from the whole system. So first of all, what you can find here, the size of the system is obviously pretty small. Secondly, they are detached from each other. And finally, you could employ or deploy this system even the roads that doesn't have any power, because it doesn't need a direct power supply. So it could basically anywhere in our highway in all over the United States. So now, so this is the node it looks like, and I have a copy of with me so that you can touch and feel. You can see how the node looks like. So you can see it's a very small one, and my student is going to pass. And this is the smart road sensor that we have been designing. Once again, it not only can detect the vehicle, it also can identify, has a very small footprint, and it also doesn't need to be connected with wire. That means it's completely wireless. Now, how do we test the whole system? Everything starts in the lab at first before we go to the road, isn't it? So this is the test bed that we have designed in our campus, in our lab. So when we are buying so many RC cars, one of the faculty saying that you guys having lots of fun with these cars, but ultimately we are using for detecting the vehicles. So what you see there, we have lots of toy cars, and then we created a track, and we put our sensor in 2 places. So for example, one sensor here and another sensor here, And then what we do, we pass the car on top of the rail and try to detect, first of all, detect and identify. Now, you asked me that, so each of the vehicle we are going to, we try to identify them. So let's try to, let's take a look at video. So this is the smart track or the road test that we'll be doing at, in our lab. And you'll hear from a couple of my students.
Hi, I'm Tim Shuck, one of the graduate students here on the project. What we're trying to do at this stage is we've verified the vehicles and the RC cars and the ability to classify each one of those vehicles. So the next stage, what we're going to be doing is actual vehicles. We need to take some measurements on those vehicles, and preliminary data suggests that we are able to literally separate those vehicles. So we should be able to identify them based off of their magnetic signatures.
There's the board here. The new board is the 3.1, which is this one. And we have the node analyzer. And then we have the accelerometer. And over here we have the receiver. So ideally what we're trying to do is populate the board, troubleshoot it, and then put it to work and see if we can get the reliable data from the transmitter point of view to the receiver. And that's how it works around here.
Hi, my name's Harold. I'm the lead for the software team in charge of vehicle classification. And so our goal is to basically implement a number of machine learning algorithms that we could use to integrate into our wireless sensor node to detect and classify vehicles. And so how we accomplish that is that we gather a subset of data consisting of multiple vehicles, and we use that data to train our implemented machine learning algorithms. And once we do that, we can verify the performance of each of our machine learning approaches by using a set of data from the same vehicles to test the performance of these machine learning algorithms.
So now comes the fun part. You'll see that we're trying to detect it.
This is our first car. Go ahead and run. Very good. Next one. Can you remove that one? That's the second car. Very good. And the third car. Very good. And this is the fourth car. That was run out of battery earlier. Very good. That was the yep, very good. The sixth car.
Okay, so I'd like to ask you at this point, what do you think? How are we detecting all these vehicles, all these small RC cars? Any idea? Wait, okay. So anybody else?
Speed.
Sorry?
Speed.
Speed, okay. How? I mean, first of all, I got a couple of answers. They're not, close. So first of all, there is no camera there. Okay. So as a bit earlier, I said, for example, let's go back. In the node here, we have a magnetometer, and that's very tiny, like a dot of a pen. That's the size of it. What magnetometer does is check the distortion of the magnetic field. As you know, Earth has a big magnet inside, so Earth has a big magnetic field. Even if you just move a small, very small, tiny iron on top of it. So for example, if I don't know whether it might have little bit iron or so, if I move something like that, it's creating a vibration of earth magnetic field. So just trying to make sure, we are trying to read the vibration it makes in the earth magnetic field, and based on that we try to detect the vehicles. So that's the main part that we are trying to do. So now, as you can see, in the left hand side, when we run a vehicle on top of this sensor, the small sensor, it basically record the magnetic field distortions. Obviously, we have to collect not one for each of the vehicles, for many of them. So we collect many of the samples. That means the signature that it produces when running on top of the magnetic sensor. So what kind of magnetic distortion it can produce. So once we get, for example, a sufficient number of data from it, then we do signal processing. I'm not going very in depth of it, and we understand what kind of feature that we can get out of these signals, like for example, like mean, max, the peaks, and so on. So all these features that we extract, and by using that feature, we then identify the vehicles. Now, this whole thing is, I think you have heard one of the terms that you use many places right now is called machine learning. So we use the machine learning. So we give the data to the system and ultimately try to identify each of the vehicle from these features. Now, the way it is done, we need to have a very low computation inside the sensor, because if you compute too much, it will kill the system because it's underneath the pavement. So you don't basically run it very, very high computation there. So that's why your algorithm need to be so tailored so that it doesn't compute too much, and also it doesn't compute too less so that it cannot detect it. So this is one of the main research points that we are trying to achieve. Yes?
Wait, I have a question. Like, can't you just is it like, do you have to do all this like within the sensor node, or can you like send it to like the center?
Yeah, good question. So many of these you will do it offline. The meaning is that we collect the data and we generate this kind of diagram, or this is basically a decision tree. And then ultimately we put only this decision tree in the node. So all this is done beforehand, meaning is that the training is done beforehand. Okay, good question. So now yes?
I just have a question about the, I guess the implications of this, what you did in the remote control car that you applied to like a actual vehicle. What sort of splits, how do you want to discern vehicle type, like by SUV versus coupe versus sedan, or?
Yeah, so as I said that, for example, there are two things that we are trying to do. One is classification, one is identification. So if you think about the classification that you are talking about mostly, that there are 13 type of classification from federal highway, and that's not that hard to do. So we can do that. But the most important, harder part is to identify, because for example, I mean, how do you identify a specific car, and what is the need for that? Because you like to make a smart road. For example, you are trying to detect a specific car on a crime scene or something like that. If you have this sensor, and if you can just basically say that I'm detecting a 2003 Hyundai Accord, and if you just put the signature inside the node, it can tell where a 2003 Hyundai Accord in the whole road system.
So the signature of a 03 Honda Accord would be different than like an 07 Accord?
Absolutely, yeah, absolutely. So that's because every car is different.
Right.
So, but I mean, can we identify it only from magnetic signature? That's it. So that's what I'm going to show you right now. So in the second video, we try to basically do it the same, I mean, the vehicle detection in our parking lot. And let's take a look. I mean, obviously it's not 100%, but
So this is going to be the first run of our demo. We're testing with 3 cars, 1 Chevy crossover, 1 BMW, and 1 Honda Accord.
it's not underneath.
The first car that's going to run through is going to be the Chevy crossover. And if you look at the laptop, it displays a Chevy crossover, which means that it was detected correctly. The second car that ran through was a BMW, and unfortunately it was not detected correctly. The last car is a Honda Accord, and that was detected correctly because the desktop app did not switch. So we're going to run that test around 3 to 4 times to see the accuracy of the machine learning.
So what you can see here, I mean, Hyundai Accord and BMW is both of them are sedan, and to identify them is not a easy task. So you can see that our accuracy rate is very high. So we are able to not only detect there is a vehicle here, which basically current technology try to do. So we like to have a smart road. That road just cannot just detect a vehicle. We also like to identify. So this is what you see. Obviously, I mean, this sort of technology we'll be seeing in future, not the far future. It's very soon. So now I have been working in collaboration with the city of Long Beach. So they graciously put 2 basically places in on the road, so that we can put our sensor on the real road, so that what you have seen a bit earlier was in parking lot. We like to go to the real road, and obviously, I mean, we need the permission from the city to go to the real road. So we have been working for a couple of years, and finally they put 2 small holes that has enclosure, so we can go and put our sensor. This is in front of the Cal State Long Beach in the main road. It's a very busy road, so we can put 2 sensors in the same lane in 2 different places. And you can see with my other students and people from the city of Long Beach, we are right now testing it into the real road. So with that, I like to come to a conclusion of this talk. So what we're trying to do, that we're trying to develop a micro wireless sensor system that not only can detect, but it also can identify. So identification is one of the major focus that I have been doing. So obviously you can see that developed sensor could be a potential candidate for the decade, not only 1 decade, several decade old technology that we have in deployment. It can it detect like other stuffs like bicycles and so on? Yes, it can. So I mean, you saw that in the lab. What we have tested? We have tested RC cars. Okay, and so it was able to detect the RC cars, and it was able to detect a big car that you have seen and identify. Obviously, we can detect anything that has metal if we have the, if we can train it. And it could be used for many applications that I have not mentioning here, but a couple of them, like traffic congestion management, could be used by the law enforcement to detect to specific vehicles that has did something bad, and so on. So I'm also working with the METRANS and the other funding agency to move this technology to more maturization. And these are the couple of publications that we have done in recent year about this technology. And with that, I would like to thank you all for spending time with us in this talk. And if you have any question, I'll be happy to answer, besides what you have asked.